Okay, so this is part 2 of lecture 21, and this is the main course. So today, I think I have only about half an hour. So today, we're going to start digesting something that's the essence, the very core, the heart of quantum mechanics, and it's called the Heisenberg uncertainty principle. Okay. So I said that this is the essence of quantum mechanics. That's my personal opinion. By the way, what's the essence of special relativity? That's right. It's the invariance of the space-time interval. Okay, that's the heart. Everything else comes from that. So really, okay, so first, a preamble. Okay, I'm going to say it in words. So we saw that the results of the double-slit experiment for an electron or another particle are inconsistent with the idea of a trajectory. I talked about it today. We also see that it's inconsistent with the idea of a trajectory, not only because the interference pattern, the periodic interference pattern remains even if you send one particle at a time, but there are other hints. So for example, by blocking one of the slits, in other words, by measuring a position along the particle's motion, you try to catch whether the particle passed through this slit or this slit, right? You're trying to get some positional information. Well, that changes the outcome of the experiment. You might say, well, can you do it very carefully, very sneakily? Well, if you do it, you do have to interact with the wave function. Okay, otherwise you're not gathering any information. And as long as you interact with the wave function, well, you modify the wave function, you modify the outcome of the experiment. I showed you what happens if you put a block in front of one of the slits. Well, it changes the wave function. The wave flows differently. So to get interference pattern, we must give up on knowing which slit the particle passed through. And thus, we must give up on knowing which path it followed, whether it went like that or like that. So this is another way to see that the notion of a trajectory is inconsistent with quantum mechanics. Okay, to put it another way, the result of the double-slit experiment is inconsistent. Well, I'm repeating, it's inconsistent with the idea of a trajectory, okay? If particles had trajectories, then blocking one of the slits should not affect the results. You go instead of from 2 globs to just 1 glob, but that other glob remains unaffected. And it also will, if you had trajectories, you will not have a periodic interference pattern. You will just have 2 globs or 1 glob if you cover one of the slits. So the idea of a path or a trajectory is not well defined in quantum mechanics. But what this means is that we can't know the position and its rate of change for a particle at the same time. Because if we did, we can predict where it will be at the next instant and the instant after and so on. And then we would know its path. Right? So if you know position and velocity, you can predict, you can extrapolate and predict the position at the next instant of time. And then at the next instant of time and so on. So you get a trajectory, okay? So if we know the position precisely, we will lose information about velocity or momentum. And the vice versa, if we know the velocity or momentum precisely, well, we lose information about particles' position. Okay, we can know one, but not both, because that would be equivalent to knowing a path. And this is an example of Heisenberg's uncertainty principle, and to me, it seems to be the core of quantum mechanics. So this was the preamble, okay? You might feel confused by what I said. Again, it's just a preamble. I'm trying to suggest that somehow this notion of knowing one or the other, but not both, knowing position or momentum or velocity, but not both, has to be consistent with the fact that trajectory information cannot exist in quantum mechanics. Okay. Now, the wave nature, you see that there's a lot of wave physics involved. The wave nature of quantum mechanics, it's encoded in the wave function, and that naturally encapsulates the trade-off between the precise knowledge of position and the precise knowledge of momentum. So now let's actually talk. So this was the preamble. So let's say if I stand on the end of the rope and I wiggle the rope, very long rope. Okay, so I stand here and I wiggle the rope. Okay. So I have this wave. Of course, the rope doesn't move, but the shape of the disturbance, the shape of the surface elevation, or the shape of the rope moves. Okay, so this is the rope stays stationary. Particles just move up and down a little bit, but the shape of the disturbance moves. That's the wave. So in any case, I ask you, where is the wave? Okay, and you will look at me funny. You will not understand my question, or maybe you will say, well, it's everywhere. On the other hand, I ask you, well, fine, what's the wavelength of the wave? And you will say, oh, nah, the wavelength is, yeah, I can see the wavelength is, I don't know, 10 feet. Okay. So you can give me a precise answer to the question of the wavelength, but you cannot give me a precise answer to the question of position. It's everywhere. Okay, so this is experiment 1. This is, of course, I would like to explain the Heisenberg's uncertainty principle in multiple passes. For my experiment, it should be done in multiple passes from my experience. And so, of course, this is not yet Heisenberg's uncertainty principle. This is like a simple-minded little story that builds up to it. Okay, I want to first and foremost build your intuition without too much math. Okay, now, so this is experiment 1. So this is experiment 1. Now this is going to be experiment 2. I stand and I'm going to just flick, yank. Okay, what? So I have a taut rope and I just flick. What would the rope do? Well, if I just flick once, I send a pulse. Okay, send a pulse. Okay, or maybe it will have like little wiggles, or maybe it will have some sort of a shape like that, and then it will move like that, right? I send a pulse, and this is periodically oscillate the end. So this is experiment 1, and in experiment 2, I just flick the end, the flick end once. Okay, so that's experiment 2. And then I say, well, okay, where's the wave? And you say, it's here. Boom, right? You can boom, you can point to a position. Obviously, at a later time, it will be somewhere else, but I will ask you a question 10 seconds after you flick. Where is the wave? And you say, here. You will be able to point. And then I say, fine. What is the wavelength? Okay. And you would say, huh? There's no wavelength. There's not a well-defined wavelength. Okay. There's not a single wavelength here. Okay. of course, by now you have already experienced this. That was the point of that very important wave lab from the previous homework. Of course, you will have already experienced that you can build up a wave shape of arbitrary form by superposing sine waves, traveling sine waves or stationary sine waves. You can build up arbitrary signals. You can build up arbitrary wave shapes. And you would say, well, of course, I understand why you say that this doesn't have a well-defined wavelength, because in order to have a pulse like this, you have to add up lots of harmonics. Whereas in the first case, in experiment 1, it's a pure harmonic. Well, if it's a pure harmonic, it has a very well-defined wavelength. Therefore, the extent of the waveform will be large. But the upshot is there is a trade-off. Between how well defined is the position and how well defined is the wavelength, or really the wave number. Okay. You saw in your wave lab that when the wave number, when the range of wave numbers that go into making up a signal is broad, the function itself, the waveform itself, is narrow. And when the range of wave numbers is very narrow, let's say go to extreme, just a single wave number, like in experiment 1, the waveform is broad. So you can see this very thing happening. So in other words, the spatial extent is inversely proportional to the range of wave numbers. Okay. See homework 4, problem 3, wave lab. Okay, very important. So again, when you have a pure sine wave, okay, so this is here only a single k is involved. Delta k is small, delta x is large. Okay. Actually, let me use a different color. For just a second, I'm going to pause. So here only a single k is involved. Delta k is small. So if it's truly a single k, the delta k is 0. And delta k is not just large, it's infinite. If there's only a handful of k's involved, well, it's not going to be a pure sine wave anymore. Okay, it will be modulated sine wave, but it will still be broad, right? So now if delta k is not 0, delta x will be not infinity, but if delta k is small, delta x will be large. And as you increase delta k, well, delta x shrinks. Okay, so here there are many k's involved. Delta k is broad and packing more and more wavelengths together, more and more wave numbers together, allows us to make the waveform narrower and narrower. And you saw why in WaveLab, because the region in space where constructive interference happens, where everybody agrees, shrinks further and further. Right? If you have a lot of people, it's harder and harder to get everyone to agree. If you have a lot of different wave numbers, wavelengths involved, they all add up constructively over a narrower and narrower and narrower region of space. Okay, delta x is narrow or small. Let me use the okay, agree? Does that match your experience? And again, the upshot is that there's a trade-off between how well defined is the position and how well defined is the wavelength or wave number. And we can summarize that trade-off like that. And another way to write that is delta x, delta k is some number. It's usually of order 1. The order of magnitude of that number is 1. But okay, some constant. So this is, let me say, not number, but some constant. Okay. This is just math. This is just math. Now a little bit of physics. Now let's introduce a little bit of physics. So this is just wave math. Nothing to do with physics. This has been very well known since 19th century, long before quantum mechanics. Physics. P equals h bar k. So therefore, delta x, delta p is proportional to h bar. Actually, sorry, let me go back to the math. More precisely, delta x, delta k is bigger than or equal to some number. Some number. And that number is usually 1-ish. Okay, so let's say just some number of order 1. So why bigger than or equal to? Because you can always come up with some kind of a funny wave with holes and gaps and things like that, for which this expression is bigger than 1. You can make this product as big as you want, but you cannot make it arbitrarily small. Okay, this is sort of a result from the theory of waves. So I don't want to dwell too much on the math that will confuse you. The equality sign holds for something called a Gaussian pulse. Okay, so basically a bell-shaped curve that goes like e to the minus x squared. I don't want to dwell on the details right now. But in general, there's an inequality, right? So as you shrink the pulse width, you must increase the range of wave numbers involved, okay? And there's sort of the lower limit, right? You can increase it more, but not less, right? So there's kind of a trade-off. Okay, so now physics. P equals h bar k, k. And so therefore, if I multiply everything by h bar, then delta x delta p must be bigger or equal to something that's proportional to h bar. And it turns out that it's h bar over 2, okay? So I'm not proving it. I'm trying to motivate where this comes from. Okay, so you see quantum mechanics puts physical cloak over this math. And it tells you that if you have a wave function that's a pure momentum wave function, for example, the plane wave, well, that plane wave is infinitely broad, but if you have a wave function that's made up of multiple plane waves, multiple k's, i.e., you're mixing in the wave function of different momentum states. If you ask what is the momentum of that particle given by that superposed wave function, it's not a single value of the momentum. We will study later that if you do measure momentum, you might get one or the other value, right? So there's a mixture of momenta involved. Well, then your delta x starts to shrink. And this is called the Heisenberg's uncertainty principle. Let me say a few more words. Again, I promise we will do this in many layers. There's a lot to understand here. This is my attempt to introduce this idea to you. What is delta x? The delta x is the width of the wave function. And so if I have, let's say if I have a real wave function, like what waves are we interested in? We're interested in wave functions, right? So I have a wave function that looks like this. Well, so here's our delta x. Okay, so when we talk about delta x, it's the width of the pulse, the width of the wave. What waves are we interested in quantum mechanics? Wave functions. What's a wave function good for? Well, it gives us probabilities, right? So probability is a function of x equals the square of the amplitude of the wave function. Now, if you square the amplitude of the wave function, it will look something like that. And again, it's delta x. Okay, so now we're adding the statistical aspect. Okay, so this is statistical aspect of the wave function. And if the square of the amplitude of the wave function takes on the meaning of probability distribution, then what is the width of a probability distribution? It's the standard deviation. So delta x is really the standard deviation. What does that mean? It means that if you have an ensemble of experiments, in all of those experiments, the particle is described by this wave function. Okay, and you put a bunch of graduate students for 5 years and you ask them to measure position again and again and again in the same experiment. You prepare all particles using the same experiment. You will collect statistics that will look like this position distribution. Okay, and sometimes you will find the particle here, sometimes you will find here, even rarely here, almost never here, almost never here. So you will have an accumulation of statistics of your outcomes. There will be some average position, there will be some spread of positions. And the measure of that spread is the standard deviation. Okay, so now we're connecting it to statistics. First, it's just waves, but now what's waving? Okay, it's one of your questions in the video quiz. Well, it's the probability distribution, right? So delta x, the breadth of the wave function, therefore measures the breadth of the probability distribution, which is really the standard deviation. Delta X is just the standard deviation of position measurements. Delta P, which is proportional to delta K, right? So if you build your wave function by superposing waves of different Ks, like in your wave lab, you see there's a spread of Ks and there's a spread of X. If you have a spread of K, you have a spread of momenta. What does it mean physically? It means the following, that if you prepare your particles to be described by this wave function, then when you make not position measurements, but when you make the momentum measurements, you will again get some kind of a distribution. The spread of momenta is the standard deviation of momentum measurements. And so what the Heisenberg uncertainty principle says, okay, this is the statistical meaning, is that there's a trade-off between how well you know the position and how well you know momentum, statistically speaking. Okay, so let me emphasize that again. Let's be clear what this means. So this is standard deviation, equals measure of uncertainty. If the standard deviation is very narrow, you're almost certain you're always going to get more or less the same value. If it's large, there's a lot of uncertainty of position measurement outcomes. And this is measure of uncertainty of momentum measurement. Okay, so the product of uncertainties turns out to be, has a lower bound. Okay, again, it's the equality holds for very special type of waveforms called Gaussian waveforms. We will discuss them, but it can never be lower. The product of uncertainties can never be lower than h bar over 2. Let's be clear what this means. Like position measurements, momentum measurements yield precise answers when you make a measurement. The spread here refers to the fact that measurements on identically prepared systems do not yield identical results due to randomness of quantum mechanics. So in one experiment, I make a measurement, boom, I found a particle here. It's a specific position. But in the next experiment, for the electron gun that fires in exactly the same way, the particle will be found here, in the next experiment here. Okay, so you have a spread in the outcomes. Okay, now you can, if you want, prepare a system such that the repeated momentum measurements will all lie very close. Okay, to do that, you have to prepare electron to be in the wave function described by the plane wave. But you will pay a price, because then the position measurements will be widely scattered. Or you can prepare a system such that the repeated position measurements will be very close together. Okay, wave function will be a spike. But in this case, you pay a price. In this case, the momentum measurements will be widely scattered. So you can say, well, I prepared my particle to be in a well-defined position state. Okay, then when you make an ensemble of momentum measurements, particles thus prepared, you'll get a very broad range of momentum outcomes. Or you can say, I prepared my particle to be in a well-defined momentum state. Well, then, fine, if you measure momentum, you will just see that one and the same value. But if you were to measure the position, you will get a very broad distribution of positions. Okay, that's the Heisenberg uncertainty principle. You can also repair a state with both position and momentum not too well defined. Okay, for example, a long wiggly line with lots of bumps and potholes, no periodic structure. Heisenberg uncertainty principle does not prevent it. It only puts a lower limit on the product of the uncertainty of position and the uncertainty of momentum. So I would like to give two examples. This might be very theoretical. So let's try to bring the sanity back. So let's apply Heisenberg uncertainty principle to a microscopic and a macroscopic system. Let's go back to our dust particle and an electron. Okay, two examples. Dust particle. This will be very instructive. This is a macroscopic system. I don't know, this is like to use the word system. It's a jargon thing. Okay, so dust particle, so again, mass equals 10 to the minus 15, 10 to the minus 15 kg, diameter, I don't think, well, yeah, diameter is 1 micrometer equals 10 to the minus 6 meters, and velocity equals 10 to the minus 3 meters per second, yeah, millimeter per second. Momentum equals mv, it's not relativistic, equals 10 to the minus 18 kilogram meters per second. Okay, now, well, if you have a micrometer particle, how accurately can you measure its position? A good position measurement would be able to identify its position to within a range that's much less than the size of the particle, right? If you have a baseball, you want to know the trajectory to within a millimeter, but not to within the size of the baseball, otherwise it's all wobbly and fuzzy. So let's say a position measurement may, somehow it's hard for me to spell that word. It's one of those things like, yeah, position measurements. Is accurate to within 0.01 micrometer, 1/100th of the size of the dust particle. It's really good. Okay. Then Heisenberg uncertainty principle says that the spread in position measurements determined by quantum mechanics, not by your experiment and not by quality of your apparatus, must be bigger than or equal to 2 delta x. Now h bar is very small, you see. So now if I just use orders of magnitude, I'm not going to put in, I'm not going to cross the t's and dot the i's. I'm just going to do an order of magnitude estimate, 10 to the minus 34 divided by 10 to the minus 8. 2 doesn't change it very much. This is 10 to the minus 26, 10 to the minus 26 kilograms meters per second. Compare with momentum, which is equal to 10 to the minus 18. Okay, so in other words, the spread in the momentum measurements, the lower limit on the uncertainty of momentum measurements is incredibly small in comparison to the momentum itself. That's what it means to say that it's small. It's small in comparison to the momentum itself. Momentum measurement. or in students' words, it's a small percent error. Of momentum. This is the lower limit. In other words, this is a negligible uncertainty. So for all practical purposes, we can talk of a trajectory of a dust particle as if it were certain. It's not. There's quantum mechanics lurking in the background. But you see what's going on, right? You see what happened, that the uncertainty in momentum, it's not zero, but it's very small in comparison to the momentum itself. It's almost like we know the momentum, and it's almost like we know the position, because position, the uncertainty in position measurement is much less than the size of the particle. Now compare with atomic electron, with atomic electron, i.e. electron in an atom. And you will see why it matters that it's an atom. So this is microscopic. Okay, electron is confined to the size of an atom, 0.1 times 10 to the minus 9 meters. That's why it matters that it sits inside an atom. We discussed that the context matters. And if you apply the mass and you use the typical value of the momentum of an electron atom, after the dust settles, Heisenberg's uncertainty principle says that delta P is something like 5 times 10 to the minus 25 kilogram meters per second. And you will say, oh, this is tiny. Okay, but electron's momentum, it's something like h over lambda. What's the wavelength of an electron in an atom? It's comparable to the atomic dimensions, right? So wavelength is something like atomic dimensions. These are estimates, okay? You might think that this is too wishy-washy. No, these are estimates I'm doing, okay? So it's momentum of the electron is about 10 to the minus 24 kilogram meters per second if you plug in the numbers. Now you tell me, is the uncertainty in momentum small or not? Okay, percent error is of momentum measurements is not small. In comparison to 100%, right? Okay, and if you want velocity, well, you can divide this 10 to the minus 24 momentum, 10 to the minus 24 kg meters per second by the mass, and you will see that the spread in velocity, note m equals 9 times 10 to the minus 31 kg, so delta v becomes 6 times 10 to the 5 meters per second. It's not negligible, okay? In fact, it says that the velocity measurements of electron in an atom will be spread by something like 10% of the speed of light. This is another example how, while quantum mechanics applies to everything, for macroscopic things, those quantum uncertainties, that quantum fuzziness, can be neglected. For ordinary objects, ordinary macroscopic objects like dust particle, you see that, well, it behaves classically. We can essentially talk of a trajectory of a dust particle without any guilt. Yes, there's a fine print. Yes, there's fuzziness, there's uncertainty, but it's very small, so we can neglect it. We kind of already encountered this, but now we see this in light of the Heisenberg's uncertainty principle. And I promise you, we will continue building this up. Okay, see you tomorrow.